started with the afternoon session, and our first speaker is Farhad Hormozdiari.
Good. Yeah, perfect.
From Eleazar's lab, and he's going to be telling us about CAVIAR.
Thanks, Matthew. Thanks for everyone for coming, and I have to say I'm very excited to be here, especially 1 hour ago I was locked down in my office, so it's much better to be here at this point. So today I'm going to talk about our tool called CAVIAR, which tries to identify the causal variants in associated regions. So let me give a brief introduction. What we do is that in genome-wide association study that we all know, it's a process that you collect individuals who have disease called cases and individuals who don't have disease called control, and then you genotype this individual, and you collect their genetic information, and if you perform some statistical tests at this process, the output will be this Manhattan plot, which the x-axis is the variant location, and the y-axis is the significance score for each variant. And the higher the correlation or the significance of that variance towards the trait or the disease. Now, the question people are interested to ask is that which of these variants are actually causal? And the concept of causal is a variance that is responsible for observing a specific peak of association in a GWAS study. So you may consider that this is a very simple problem. Just pick a significant threshold like this red horizontal line and consider anything above this to be significant and consider those to be causal. And you can see there are too many variants that pass this significant threshold, so it's not that easy to say which of these variants are actually causal. Now, let's go over a very simple example. Here I'm showing a region which have 35 SNPs on the x-axis, and the y-axis is the significance score for each variant. You can consider the minus log p-value. And the gray triangle represents the LD score, or the LD structure for this variance, and every diamond in this LD represents the pairwise correlation. And the darker the diamond, the higher the correlation between the two variants, and the lighter the diamond, the lower the correlation. Now, if I ask you which variance is causal in this region, most probably you pick the most significant SNP in this region, and you consider that as causal. In this case, actually, this is the actual causal variance, and how we know is that we implanted this region, this variant to be causal. So you can assume that by just looking at how the variants are distributed and the LD, you may have a good sense which variants are actually causal. Now, obviously not all examples are that easy. Here I'm showing you a more complicated example, which it's not easy to say which variants are actually causal in this region. Later on during my talk, I will show which variant is causal, but you can try to figure out which one is in and pick your variant that think it's causal. Now, you can consider that this problem is hard because you can see the LD becomes more dense here, so it makes it more complicated. And when you look at the scores, you can see that it's very hard to distinguish which of these variants can be causal. So there have been a method developed to try to solve this problem, and usually this process is referred as fine mapping. So fine mapping is that given the marginal statistics that you observe from the GWAS result, can you figure out which variants are actually causal? And the reason this problem is hard is due to two facts. One is the linkage disequilibrium, means that the variants are correlated. So if variants are independent, it makes the problem easier because you can break the problem to two simpler problems and solve them independently. So it makes the problem hard computationally when you have LD. And the other fact is that when you have LD, you capture the effect of another causal SNPs. So if two SNPs are in LD and one of them is causal, you will see the effect of that causal SNP in another SNP. So you don't know this effect that you're observing in this variance, is it the effect of that SNP or you're tagging the effect of another SNP. And another reason that this problem is hard is due to the fact that there can exist more than one causal variance in a region. So most existing method assumes that there is only one causal variance, but we all know that there can exist more than one causal variance in a loci. Now, the existing method that I will talk are the top K and the conditional method, which I will explain in the following slide, and then I will explain what are their limitation and why we propose our own method. So the top K method is actually a very simple method. You pick the top K most significant SNP based on the p-values. So here I'm showing that, for example, K equal to 5, you pick the 5K most significant SNP based on the p-values. So the black arrow represents the variance that is picked by this method. And I'm showing that complicated region that I presented in the beginning of my talk. Now, here I will show the answer. So the red triangle are actually the causal variants that we implanted in this region. So you can see when the K was 5, the top K was unable to detect any of the causal variants that was implanted in this region. So it's obvious that top K can perform poorly in this region. Now, another problem with the top K is that knowing the right value of K is actually very hard. we don't know in advance what is the right value of k. And trying to figure out what's the right value of k, you have to know which variance is causal. And another problem with the top k is that the algorithm completely ignores what's the LD. So no matter what LD I put here, the top k will give exactly the same answer. So it's ignoring the LD. Now, in order to solve the problem of LD, people propose another method called conditional, which actually is an iterative process. And in each step, you pick the most significant SNP as the causal variance in your set, and you recompute the marginal statistics of all the other SNPs, given that this SNP is causal. And you keep doing this till all the variants, their significance score, fall below a significant threshold. So here I'm showing this example. The red arrow represents the SNP that you picked as the causal variance, and you remove its effect. And by conditional, you just remove its effect from that SNP and every other SNP that this SNP is affecting. So then you pick the next top SNP in this region, and you keep doing this process. Now you can see if you do the conditional only twice, you can't find any of the causal variants that we implanted in this region. So you can sense that for this complicated region, both the top k and the conditional method fails to find the true causal variance. And you may consider why this is happening. And if you realize both of these methods makes an assumption that the most significant SNP is always the causal SNPs. And we want to see how much this is true. So we did a simulation. We picked two regions. One, the LD is very simple. The other one, the LD is more complicated. And we try to implant one SNP to be causal. And we try to see what's the rank of the causal SNPs. So the histogram shows the rank of the true causal variance. So you can see when the LD is simple, the majority of the time, the causal variance is actually rank 1. However, when the LD becomes more complicated, this is not necessarily true. A significant fraction of the time, the causal variance is not ranked 1. So this is the reason that both the top k and the conditional method perform poorly. So this motivated us to come up with our method. We actually refer it as CAVIAR, causal variant identification in associated region. So I won't go to too much detail of the method, but what it do is that it try to find a row causal set. So row causal set is a set that can capture all the causal variants in a region with probability at this row. So in practice, you will set this row to be a very high value, like for example 90 or 95%, and you hope that it can capture all the causal variants with probability at least 90 or 95%. Now I have to mention that this doesn't mean that all the variants in the row causal set are causal. What it means is that if you go and validate all the variants in the row causal set, with probability 90 or 95%, you can capture all of them. So a trivial solution to this problem is that just pick everything in that region as causal, as your row causal set. And with probability 100%, you can capture everything. Obviously, this is not the right answer. So what CAVIAR does, among all the row causal set, let's say 95% causal set, you would try to capture the one that has the minimum size. So what's the input and what's the output of CAVIAR? So the input to CAVIAR is the LD. As you can see, the method requires the LD because LD has some uncertainty that we have to model. And you can either compute it from your data if you have access to genotype data using plink, which is a very simple command to do that, or you can approximate it using the 1000 genome data if you only have access to some of your statistics. And the other information that it needs is the marginal statistics, like the GWAS statistics that you obtain either from other studies or you perform the statistic yourself. And the output would be a row causal set, which is the set that can capture all the causal variants with probability at this row. So let me show the output of CAVIAR in two examples. So this is the simple region actually I show in the beginning of my talk. Here, CAVIAR picked one SNP. The black arrow represents the SNP that CAVIAR picked as a 95% causal set. So for this simple region, CAVIAR picked only this variance, which actually is the causal variance. So if you go and validate it with probability 95% or higher, you can capture it. Now let me show you the more complicated example. So this is the example that both the top K and the conditional method fail. You can see CAVIAR picks 7 variants, and it can capture both the causal variance that was implanted in this region. So this simple example, actually this complicated example shows that CAVIAR performs better than the two methods. Now, obviously this example is not just one example, but in our paper we show that even like more complicated and more region in the genome, CAVIAR performed better than the two existing methods. Now, with this, I want to conclude part of my talk is that we have a method that can perform fine mapping, can detect a row causal set. That set can capture all the causal variants with certain probability that the user can define. And this is actually, you can download it from towards our website or from the GitHub. And it's actually very easy software. You don't have to need any software installed. You just download it, you make it, and you're able to run it. And there's actually a simple example that you can run it to make sure that everything works fine. And with this, I want to acknowledge the people who were involved in this project, Emre Kostam and Yoon from our lab. And I want to thank my supervisor, Eliza, and Bogdan Pasnik. And thank you for your time.